Welcome students. Myself Dr.Monika Khetarpal. I am Associate Professor of Physics in Government Dongar College, Bikaner. I welcome you all in my enlightening session of Classical Mechanics. This is the first paper of MSc Previous Physics. Today we will start our section 5. Before moving on to the next section, I am going to give you a brief review of important formulas that we have derived up till now. The first important formula, which is based on principle of virtual work, is summation Fi dot delta Ri equal to 0. Here Fi is the force acting on ith particle and delta Ri is virtual displacement. And we have taken it for n particle system. So here we have taken a summation. The summation is from I is from 1 to n. This principle states that virtual work is equal to 0. The next important principle that is derived is D'Alembert principle. It is simply an extension of principle of virtual work. Here we have shown that summation Fi minus Pi naught dot delta Ri equal to 0. According to D'Alembert, system is in equilibrium not simply because when force is 0, it is in equilibrium when force plus the reversed effect force, which has a value minus Pi naught, these two terms make a system in equilibrium. Further, we have derived the general form of a Lagrangian equation. The general form is d by dt del t by del qj dot minus del t by del qj equals capital Qj. Here capital T denotes the kinetic energy, Qj is the generalized coordinate and capital Qj means generalized force. Depending upon the number of generalized coordinate, for example, if we have n generalized coordinate, then there will be n number of such equations. Now, using the general form of Lagrangian equation, we have derived the Lagrangian equation of motion for a conservative system. The equation of motion for a conservative system is d by dt del L by del Qj dot minus del L by del Qj equal to 0. Here L is the Lagrangian of the system and it is equal to T minus V. T being the kinetic energy and V is the potential energy of the system. So this is the basic equation that we will need in our further lecture. Now I am going to discuss equivalent one body problem. In this equivalent one body problem, I am having two mass points which are denoted here by m1 and m2. Let these masses, that means m1 and m2, they are situated at a distance of r1 and r2 from origin O. So, I am taking a point in between these two masses which is the center of mass of these two points. Let the center of mass is at a distance capital R from origin. And these masses m1 and m2, they are at a distance of r1 dash and r2 dash from the center of mass. Now, our aim is to convert this two body problem into a one body problem. For this purpose, we will find the Lagrangian of our system. As we have already stated that Lagrangian of the system is T minus V. Here T is the kinetic energy. The kinetic energy will be equal to kinetic energy of motion of center of mass and the kinetic energy of motion about the center of mass. That means kinetic energy will comprise of two terms. Here the first term, which is the kinetic energy of motion of center of mass, it will be equal to half sum of two masses m1 plus m2, and we have assumed that distance of center of mass from origin is capital R. So velocity will be r dot, hence kinetic energy will be half m1 plus m2 r dot square. This is the kinetic energy of motion of center of mass. The other term is the kinetic energy of motion about the center of mass. M1 particle is at a distance of r1 dash from center of mass. Hence kinetic energy of this mass will be half m1 r1 dash prime square. Similarly, the kinetic energy of the mass m2 will be half m2 r2 prime dot square. So my Lagrangian will be, first is the kinetic energy of motion of center of mass, and these two terms are the kinetic energy of motion about center of mass minus the potential energy. Since the system is conservative, the potential energy will be a function of distance between these two masses, and let the distance between the two masses is r. Now this distance r can be expressed as, we can see from this diagram that this r is equal to, according to the vector diagram, r1 minus r2, and when expressed in terms of prime coordinates, r will be equal to r1 prime minus r2 prime. Now in our Lagrangian we have a large number of generalized coordinate r, r1 prime, r2 prime, r. In order to reduce them, we will convert r1 prime and r2 prime in terms of r. For this purpose, we will use the condition of center of mass. We know that center of mass is a point where body balances. That means m1 r1 prime is equal to m1 r1 prime plus m2 r2 prime is equal to 0. So from here I can find the value of r1 prime, and using this r1 prime value I am substituting r1 prime here in my equation 1 in order to get the value of r. This r will come out to be m1 plus m2 upon m2 r1 prime. From here I have find out the value of r1 prime. Similarly, I can obtain the value of r2 prime. So using r1 prime and r2 prime in terms of r, I get my Lagrangian as L equal to half m1 plus m2 capital R dot square plus half m1 m2 upon m1 plus m2 whole square r dot square plus half m2 m1 upon m1 plus m2 square r dot square minus Vr. Now from these two terms, second and third term, I am taking a factor m1 m2 upon m1 plus m2 whole square common, and solving I get the value Lagrangian to be equal to half m1 plus m2 r dot square plus half m1 m2 upon m1 plus m2 r dot square minus Vr. Here we have taken two particle system. These two particles have mass m1 and m2. Hence in our system the total mass will be, if expressed as capital M, it will be equal to small m1 plus small m2. And we know that reduced mass mu is expressed as m1 m2 upon m1 plus m2. So my Lagrangian of the system will be half m capital M r dot square plus half mu r dot square minus Vr. Here we have two generalized coordinates, and that are capital R and small r. So in order to solve the Lagrangian equation, we have two expressions. First of all, I am writing it for capital R, choosing my generalized coordinate Qj to be capital R. The Lagrangian expression will be d by dt del L by del R dot minus del L by del capital R equal to 0. From here we can see that differential of L with R dot is equal to mR dot. So this expression takes the form d by dt mR dot, and derivative of L with capital R is 0. Now the Lagrangian equation becomes d by dt mR dot equal to 0. On integrating it, I will get mR dot equal to constant. Since mass of the system is constant, from here we can conclude that R dot will be equal to constant. That means velocity with which the center of mass moves is constant of motion. Now I am taking my another Lagrangian equation that will be obtained by using generalized coordinate as small r. Now in this case the expression will be d by dt del L by del small r naught minus del L by del small r equal to 0. My Lagrangian was this expression. So differentiating it with small r dot, this will give me mu r dot. I have to solve for dl by del r. Del L by del R will be equal to minus del V by del R. So putting all the values, I obtain my expression, Lagrangian expression, as mu R double dot equals minus del V by del R. We know that minus del V by del R, it represents force. Hence it can be expressed as mu R double dot is equal to force, which is a function of distance between these two particles. Hence this represents the equation of motion for a system which is having a interparticle distance small r. Now since we have derived that center of mass, which is located at a distance of capital R from origin, it moves with constant velocity. Hence in our Lagrangian expression, since this is our Lagrangian, we know that mass of the system, it remains constant. That means capital M is always constant, and we have shown that R dot is constant. So this is a constant term in Lagrangian. So we can ignore this term because it will make no change in equation of motion. Hence we are removing this term from Lagrangian. So we are left with only two terms, which are half mu r dot square minus Vr. We can see that this is Lagrangian for a system of a single particle which has a mass mu. So we have reduced our two particle problem into a one body problem which is having a mass mu and which is moving at a distance r from a fixed point. Hence, we have attained a condition where a two body problem can be reduced to an equivalent one body problem. Thank you students for watching.